to northern Europe. It moves about 40 million cubic meters of water per second and warms the atmosphere in the north at the same time. One reason for Europe's mild climate. In the Arctic Ocean, the water cools, becomes heavy and sinks into the depths, where it flows south again. If large amounts of ice melt in the north, or there's increased rainfall, this changes the temperature and salinity of the water. It loses density, and the deep current is disturbed.
You don't have to imagine it like in some Hollywood movies, where the whole Earth suddenly stops, or the currents, because we will always have the rotation of the Earth and the winds. But the winds also change as the Earth warms, and so do ocean currents.
Such changes have already been measured. In recent decades, the Gulf Stream has weakened slightly. Measured data that match climate models. However, the observations are not yet sufficient to rule out a short-term fluctuation. The Gulf Stream is part of the thermohaline circulation that stretches across the globe. This conveyor belt transports thermal energy and nutrients on which entire ecosystems are based, and influences weather cycles all over the planet. If the researchers' fears are confirmed, this would change the familiar weather patterns to which people and ecosystems have adapted for centuries. Water constantly evaporates from the oceans into the atmosphere, an important factor in the natural greenhouse effect and in the Earth's water cycle. But the warmer the oceans and atmosphere become, the more water evaporates. Cyclones, which occur regularly in the tropics, will then have available more water vapor and condensation energy. They will transport more moisture, become stronger, and remain stable for longer. Researchers have not yet found that hurricanes, typhoons, and cyclones are becoming more frequent due to climate change, but that they do increase in intensity and range. With more energy, they can go deeper inland and cause more destruction.
Earth observation has been at home in meteorology for many decades. The use of satellites for short-term weather forecasting in particular, but also for medium-term weather forecasting, is of enormous importance. And that, of course, has great significance in extreme events as well. We see relatively precisely how extreme events, such as hurricanes, develop. And that is, of course, necessary for evacuation efforts, where data play a contributing role.
Extreme weather events also frequently occur in temperate latitudes. For example, when weather conditions remain unchanged for days or weeks. One reason for this is the polar jet stream. The strong wind field moves warm air from the tropics northwards and cold air from the pole towards the equator. In doing so, it's steered eastwards by the rotation of the Earth. Its stability depends on the temperature and air pressure gradient between the equator and the poles. If the gradient becomes smaller, the jet stream can meander further north and south. High and low pressure areas bring heat waves or heavy rain that can last for days to weeks. Such fluctuations occur occasionally. However, there is concern that the warming of the Arctic could affect the dynamics of the jet stream. In July 2021, a stuck low-pressure system caused dramatic events in western Germany and parts of Belgium. Regionally, more than 150 liters of rain fell per square meter. The water collected in the river valleys, with disastrous consequences. More than 200 people lost their lives in the storms in Germany and Belgium. The question of the influence of climate change quickly arises, but it's hardly possible to conclusively attribute individual extreme weather events to global warming. Catastrophes like these are rare, so very long observation periods are needed to be able to read trends. What is certain, however, is that climate change creates conditions that favor or intensify events like these. Due to higher temperatures, more water evaporates into the atmosphere. Warmer air can absorb more moisture. each degree of warming brings 7% more water. Damages are correspondingly higher.
We currently experience in Germany three things above all when we talk about extremes. One is the heat waves. Then there is extreme drought, especially in eastern Germany. And then on the other hand, we also see that the heavy precipitation continues to increase. And this refers above all to the very short, heavy downpours.
In order to prevent further increasing of extreme weather, climate change must be limited as much as possible. But even then, enormous challenges remain for people and infrastructure. After all, the global mean temperature is already 1.1 degrees Celsius higher than it was in 1900. And the effects on sea levels, ecosystems, and the weather can be felt and measured in many places. Climate change brings increased storm surges, heat waves, and droughts. But humans are not defenseless against it. There are still ways to reduce emissions and slow down warming.
I think what humanity doesn't realize is that it is ultimately sawing off the branch on which it is sitting. Because at the end of the day, we are also cutting off the possibilities to feed ourselves. If we continue to pollute the oceans, not only through climate change, but also through overfishing, through the input of plastic waste, all of these things, then a fundamental pillar of the world's food supply will fail. In the same way, if the climate changes dramatically, agricultural production will suffer significantly, and another pillar of the world's food supply will thus be at risk. Nature will continue to exist, humanity may not. And it is up to us whether we want to continue to exist in the long term or not.
Today, almost 8 billion people live on the planet. They all depend on clean air and water, fertile soils, and stable weather conditions. Plants are a cornerstone of the Earth's climate system. They make up the majority of human nutrition, stabilize our soils, and produce the oxygen we breathe. Plants form a crucial pillar in the carbon cycle. To make the distribution and activity of plants visible, some satellites can detect the infrared radiation reflected by plants. A quarter of the land surface of our planet is covered by forests. They bind large amounts of carbon. In spring, plants extract a lot of CO2 from the atmosphere in order to grow. In autumn and winter, however, photosynthesis ceases in temperate latitudes. Especially in the northern hemisphere, where the majority of temperate forests are located, CO2 turnover therefore fluctuates seasonally. Researchers at the Helmholtz Center for Environmental Research in Leipzig want to know exactly how much CO2 is absorbed, stored, and released by forests. They have set up a research station for this purpose in a forest near Magdeburg. Meteorologist and climate researcher Corinna Rebmann heads the project. The forest is peppered with measuring instruments. They determine how much carbon dioxide is absorbed by the soil, record tree growth, and the chemical composition of the foliage. The centerpiece of the station is the all-surpassing measuring tower. Leonie Röhler is also part of the team. Today is the research assistant's first time at this research site.
So it is important how much carbon is fixed by such a forest. In this case, a mixed deciduous forest, depending, for example, on the available radiation. We compare this with other forest ecosystems throughout Germany, Europe, and even worldwide.
In order to understand the complex processes, measuring instruments are distributed over the entire height of the tower. Light irradiation, temperature, humidity, precipitation, wind, and air composition are documented and evaluated every half hour. To reach the main measuring device, the researchers have to climb to lofty heights.
We are now 50 meters up the tower. The tower is so high because we have to take measurements well above the vegetation. And that's why the centerpiece is up here. This is a very sensitive anemometer in combination with a gas analyzer to determine the CO2 and water vapor concentrations in this case. And what we want here above all is to determine the biomass growth, that is, how much carbon is sequestered here in the forest.
Not every forest binds the same amount of carbon. To be able to compare different forest types, there are similar measuring stations all over Europe. It's also about identifying which forest types are better able to cope with climate change. The dry summers of 2018 to 2020 provided Corinna Rebmann and her team with particularly clear data.
It was indeed widely reported in the media that the spruce population in particular has suffered greatly in recent years due to the drought. We've also noticed that here, the forest has also had significant losses in productivity. Nevertheless, we do not yet have a dying forest here, as opposed to many other spruce forests that were sensitive to the drought, then to the bark beetle, and actually died and had to be cut down. It is not yet possible to say that here. However, it was clear that after 2018, productivity, which is the biomass growth or carbon uptake, was significantly reduced.
Germany-wide, the damaged area is about 277,000 hectares, which is more than the total area of the Saarland. About 25% of the forest in Germany consists of tree species that are particularly sensitive to drought and heat, and thus also to climate change. Despite some unusually strong dry periods in Europe, forest development varies worldwide. Satellite images show that the Earth has become greener. This is also related to the higher CO2 content in the atmosphere. It can promote plant growth to a certain extent, but only as long as enough water and nutrients are available at the same time. But also the increase in agriculture, nitrogen fertilization, and afforestation are making the Earth greener as well. The shifting of climate zones also plays a role in the greening trend.
We also see this effect in the polar regions, for example. The areas where glaciers recede, where soil is suddenly exposed, will naturally also experience plant growth, which you can see there then too. This can be observed in Greenland, for example, and in other places, even in the Antarctic. There are now areas where we see certain ground signals and suddenly also some vegetation. This is the normal effect that has to do with climate change.
Rico Fischer also makes use of the data from the Hohes Holz Research Forest. The mathematician plants virtual forests. Digital leaves, branches, and trunks are created in his visualization laboratory at the Helmholtz Center for Environmental Research. The model forests are intended to simulate real forests, and above all, to calculate their productivity under various environmental factors.
The forest ecosystem grows very slowly, and through such models, we have the possibility to understand the processes in the forest, for example, how a forest reacts to drought. But we can also use the models to forecast into the future. What happens if we have a much warmer climate in the future, or if humans also have a much stronger influence on the forest? Models can really be used for this because we can easily simulate 50 to 100 years into the future. Of course, that's not so easy now with a forest experiment like this. We could also just wait and see. But by then, it may already be too late. That's why we use the models to forecast at an early stage. How can the forest change in the future? And how might even people help to make the forest future-proof?
A particular challenge in modeling is the individual approach. It's not the forest as a whole that is simulated, but each individual tree is represented in the model. This allows modelers to exchange individual tree species and represent different forest types. Measurement data from research stations around the world are growing into complex forest models. And there's another dimension that gets added: remote sensing. To observe forests from above, methods range from simple satellite images to scanning with laser beams to radar measurements. These can survey forest areas even at night and when it's cloudy. The view from space has provided forest research with fundamental insights.
The first big results may sound a bit silly, but first of all, we determined where the forests on Earth are. Until now, we didn't really know, and it's still difficult because we have a lot of cloud cover. But the goal was to create maps showing where there is forest on Earth. And now we try to update these maps every year to see how the forests are changing, where is forest being added. Unfortunately, we can see more forest being lost, either through legal or illegal deforestation.
Tropical forests account for about 45% of the world's forest area. They are home to half of all animal and plant species living on land. Nobody knows exactly how many species. In 2020, about 4.2 million hectares of primary tropical forest were destroyed worldwide. This corresponds to an area roughly the size of the Netherlands. The Guardians in space also keep an eye on our forests. Sentinel-2, ESA's second Sentinel mission, consists of two identical satellites that fly along the same orbit, but 180 degrees apart. This allows the pair of satellites to scan the entire globe within 5 days, with the exception of Antarctica. The satellites also pick up the range of infrared radiation emitted by plants. This makes it possible to record images that provide information about the distribution and condition of plants.
What we are actually seeing is that there are almost no ecosystems left on planet Earth that have not been directly or indirectly reshaped by humans, and partly in devastating ways. Devastating here means that natural ecosystems are simply eliminated to make production sites for food cultivation. Palm oil is, of course, a well-known example, but there are also others. Development of farmland for grazing. There are many other issues and countless examples. But we simply can't bring back a primary rainforest quickly. If it is cut off, then it is gone for the time being. And from what we know, it takes decades, if not centuries, to restore the diversity of plants and animals. And when a species is extinct, it cannot be brought back. And that is a loss for the whole of humanity, a loss for the whole planet. And this must be avoided at all costs. It is a very fundamental lesson that concerns us all.
When forests are cut down, this often triggers domino effects that further destroy the forest. Forest edges are much more exposed to sun, wind, and erosion, causing even more trees to die. In addition, there is a self-expanding infrastructure of forest destruction.
On the satellite images, you see big roads and side roads branching off, eating their way into the forest. And that not only leads to more deforestation, but also to more degradation of the forest. There aren't that many primary forests left anymore. Their number has decreased by 1/3. Humans already influence most forests one way or another, and that's where I think we need to start, by protecting more forests. And once the forests are protected, they'll also keep functioning as a carbon sink, which is again important to mitigate climate change.
Already today, mitigating climate change is necessary. The 10 hottest years since weather recording began have all occurred within the last 20 years.
Here in Germany, too, we see extremes on the rise. The best example is the so-called heat days. These are days when the daily maximum temperature reaches or exceeds 30 degrees Celsius. And they have been increasing massively in recent decades.
This is an increase that has mainly been felt by farmers in Germany. Hot, dry summers have parched the soils to the depths in many places. In 2018, crop losses amounted to about 77 million euros. But even cities, where concrete and asphalt store heat particularly well, are increasingly groaning under heat waves.
In Hamburg, for example, There had never been an extended heat wave before 1994. That is, 14-day heat waves in which the average daily maximum temperature is 30 degrees Celsius or more. And we also see other large cities in Germany where this has only occurred in the recent past. And that alone is an enormous burden for our ecosystems, but of course also for the human body.
A burden that can be fatal. In 2003, over 7,000 people died in Germany alone as a result of the heat wave caused by high-pressure system Michaela. Across Europe, the number of heat victims is estimated at 70,000 people. And such events are becoming more frequent. In Germany today, there are on average 11.1 heat days per year, 3 times as many as in the 1950s. Even if it does not seem so at first glance, heat waves are among the most serious natural disasters in Europe. Hot and dry summers also increase the risk of forest fires. Even in ecosystems where fires are part of a natural cycle, dry periods cause fires to become more frequent and extensive. The fire seasons are getting longer. Moreover, 90% of all forest fires are started by people. The devastating wildfires in Australia destroyed about 21% of the country's total forest area between June 2019 and March 2020. It's estimated that about 3 billion native animals perished in the flames. The probability of devastating fires increases by about 30% as the climate warms. Experts speak of an increase in fire-favorable weather conditions. In 2020, about 40,000 square kilometers burned down on the U.S. West Coast. The prolonged drought, coupled with strong winds, caused at least $10 billion worth of damage.
Of course, it is also clear that an increasing drought and less precipitation overall increases the propensity for large, devastating fires. And there is a certain connection with the bigger overarching trend that can be recognized. But in individual cases, that is always a mixture of different effects that play a role. So you have to take a close look at the regional land use systems. But overall, where it is drier and where there is less water, there is an upward trending exposure to fire. And satellites can see that, of course.
Detecting and monitoring forest fires from space is one of the core competencies of the American weather satellites GOES-16 and GOES-17. With 16 spectral bands, GOES-16 can measure aerosols and clouds in the atmosphere and even detect thunderstorm lightning. With the help of the most precise infrared measurements, it can also identify the smoke clouds of volcanoes and fires, and thus make a fundamental contribution to detecting fires early and supporting their suppression. It was also GOES-17 that in January 2022 filmed one of the most powerful eruptions in recent Earth history, the eruption of an underwater volcano in the Pacific archipelago of Tonga. GOES-16 and 17 come from a family of satellites that have been observing the Earth since the 1970s. The two satellites, divided into a Western and an Eastern observer, are in geostationary orbit at an altitude of 35,000 kilometers. They move in sync with the Earth's rotation and always keep the same section in view. Together, they cover more than half of the globe, from the west coast of Africa to New Zealand. 2 more satellites are planned. To survey the Earth as a whole and to understand its interrelationships globally has only really been possible since the beginning of space travel. For the first time in human history, digital networking and complete observation of the Earth's surface offers the chance to truly understand our impact on our home planet. And by now, it's enormous.
The beauty of this planet is really in great danger at the moment. This can be said without exaggerating or being alarmist, because the 8 billion people, trending upwards, all want to live well. And living well means having access to resources, to food, to water, to technology, to communication, to use all the conveniences that life offers us. And we know that overall we are consuming resources today that are simply not sustainable. This means that we are currently simply consuming more resources than the planet can actually provide. We consume 3 Earths per year, where we really only have 1. And I think that in our reality in the cities, we don't really see it, but it truly is a very big task. And the Earth observation makes that visible. The satellites see that. They document that seamlessly. No one can shirk responsibility.
Climate change and human interference in natural environments are causing major damage to ecosystems worldwide and the loss of thousands of species. Of about 8 million animal and plant species, 1 million are threatened with extinction. The reasons are mainly habitat destruction, overexploitation, pollution, and climate change. It's the most extensive extinction of species since the end of the dinosaurs. The changes to the Earth's surface caused by humans can now also be tracked on Google Earth. With the help of data from the Copernicus program and NASA's Landsat satellites, the software developers have added another dimension to their virtual globe: time. In this way, some of the most extreme changes on our planet can be experienced in a time lapse. With the help of around 24 million satellite images, the application shows the Earth's surface from 1984 to 2020 within a few seconds. The short time travel makes it obvious how strongly and at what furious pace humankind has changed the Earth within just the last few decades. To better understand the changes in our atmosphere, the individual factors are summarized in models. The more information is available, the more realistic the climate can be modeled. Processing the mounds of data is a challenge that only a true mastermind can master. The Mistral supercomputer from the German Climate Computing Center in Hamburg is such a mastermind. With the help of its 100,000 processor cores, complex Earth models can be created that provide information about how the individual factors in the climate system are linked to each other. The German Climate Computing Center, or DKRZ, is one of the few institutes with such computing power. It currently pursues the PALMOD project, in which the Earth's climate is to be modeled 120,000 years into the past. Literally, a mammoth task.
The background is that we can expect dramatic climate changes in the future. And what is important in this context is simply whether these certain processes that we have reconstructed in the past, such as very rapid sea level rises due to the breaking apart of the large ice sheets, such as in Greenland and Antarctica, can also happen under today's climate conditions. In other words, we test our models to see whether they can simulate instabilities like these, for example, whether they can also represent these tipping points, which may also exist in the system. And once we know that, we can simulate the future with more confidence.
To simulate the whole Earth, the models are divided into grids. Each grid cell provides calculations, taking into account the physical laws of atmosphere, ocean, and land surface. The smaller the grid, the higher the spatial resolution, and the better the climate model. For the calculations, the project needs a huge database and corresponding storage capacities. Over 130 petabytes of climate data are archived here, and this number is growing every year. physical dynamics can be derived from the reconstructions of the past and applied to future scenarios. The models are not predictions into the future, but so-called projections. Similar to forest modeling, certain parameters, for example, CO2 emissions, are specified and the model simulates how the climate system might react to them. The scenarios form an important basis for political decisions. According to the Paris Agreement, global warming should be limited to well below 2 degrees Celsius, if possible to 1.5 degrees Celsius compared to pre-industrial times. Such a limit would be a kind of best-case scenario in the climate models.
The problem with global warming and with human-induced climate change in general is the so-called positive feedbacks, the amplifying processes. There are a number of so-called positive feedbacks which, for example, significantly amplify the effect of CO2. If there was only the CO2 effect, the climate problem would not be so big.
It's precisely in order to reduce such chain reactions in the climate system that compliance with the limits determined by the models is important. A warming of more than 2 degrees Celsius would set processes in motion that would massively increase the dangers for humans.
If the warming exceeds 2 to 3 degrees Celsius, the Earth itself will add a lot more carbon to it, because forests are burning, because the Earth's soil with microbes in it, and most importantly, the frozen ground in the Arctic will thaw, releasing much more CO2. And also because the oceans will become so warm that they will actually no longer function as CO2 sinks, but rather release CO2 as well. And we don't want to get into this acceleration, which will cause the ice sheets to melt, because then there will be an enormous sudden increase in sea level, for which we are not prepared at all.
Already today, the global temperature increase is 1.1 degrees Celsius. So there's not much time left to slow down global warming. Not all dynamics in the climate system are yet understood. Especially the effect of clouds still raises some questions. Certain clouds, especially those at low altitudes of around 2,000 meters, reflect solar radiation from space and cool the Earth's surface. Higher clouds at an altitude of about 6,000 meters stop the heat radiation that is reflected back from the Earth's surface and have a warming effect.
Clouds are highly dynamic, form very quickly, and are very much local climatological. Completely different in the high mountains than over the oceans. And the speed and swiftness at which clouds form and dissipate also makes it so difficult to describe this parameter really precisely over wide areas. And for this purpose, we also use aircraft with which we fly to certain regions to make precise measurements, which we then link with satellite data in order to develop models and subsequently, why do clouds form here and there? What effects do or don't they have?
You have to go high up to better understand these mechanisms. Very high. The German Aerospace Center operates the Gulfstream Halo jet specifically for such research purposes. The High Flyer reaches an altitude of 15 kilometers and has a range of 8,000 kilometers, surpassing almost all other research aircraft in the world. It can measure air composition even above commercial air traffic. Christiane Vogt is leading the aircraft mission Cirrus-HL. It's designed to investigate the climate impact of high ice clouds, the so-called cirrus clouds. To measure the high ice clouds, HALO has special instruments that can measure the size and shape of ice crystals, in addition to the distinctive air data boom with wind and turbulence measuring instruments.
Ultimately, this is a laser device. The laser is focused and threaded through here, and we measure the shadow images, so to speak, of cloud particles up here, which pass through the laser here. In the lower part, we measure the light scattered in the forward direction by particles that also pass through the laser focus here. And with that, we can then quantify the size and also the shape of the ice clouds.
On today's mission, Christiane Vogt and her team want to study thunderclouds near the Alps. Where passenger planes prefer to steer clear, HALO is intent on flying right in. The Flying High-Tech Laboratory analyzes the ice crystals of the thunderclouds in flight. Not a mission for weak stomachs. Apart from the experienced pilot team, there are only 4 scientists on board who monitor the measurements en route. The rest of the cabin is taken up by equipment. During the flight, the crew maintains constant contact with the ground station in Oberpfaffenhofen. To ensure the safety of the crew, but also to find the best storm clouds for the measurements, satellite images and weather reports are consulted again and again. What is also being considered is the question of whether human emissions can influence thunderclouds. About 6 hours later, HALO and its crew return, a little shaken but satisfied.
It was a great flight today. The pilots were faced with the special challenge of flying around the thunderclouds or even into them. We also wanted to make in situ measurements, but not too close, so that the ice concentration is not high enough as to lead to icing on the aircraft. That's why the tower-like thunderstorms keep popping up, and the pilots practically flew past them and into the outflow in order to enable these in situ measurements inside the thunderclouds. We can then compare this with satellite data and make assertions about the development of these thunderclouds and their effect on the climate.
With the elaborate measurements, HALO can cover the research level between ground research and satellite research, and thus hopefully contribute to an even better understanding of the climate system as well. The German Aerospace Center operates an entire research fleet to answer various questions related to aviation. Quiet, clean, and sustainable. This is the new dream of flying. Emission-free flying could look similar to this aircraft in the future. The HY-4 is a hybrid aircraft with hydrogen fuel cells and high-performance lithium batteries. So far, only 4 passengers fit on board, but it has already completed a few successful flights. Depending on speed and altitude, a range between 750 and 1,500 kilometers is possible. Whether HY-4 will be able to extend the technology to larger machines is not yet clear, but it's certainly a starting point for the further development of new technologies. And these are necessary to make air travel more climate-friendly. Currently, air travel accounts for about 3.5% of the human impact on climate change, and CO2 emissions account for just 1/3 of this. More than half are related to contrails. They occur especially in cold and high cruising altitudes of 10 to 12 kilometers.
Simulations have shown that only about 10% of the flight routes are responsible for 80% of the warming caused by contrails, which means we would specifically redirect these 10% of flight routes, for example, to fly above or below this cloud region, or use biofuels.
So-called biofuels made from plant material can reduce the formation of contrails. The impact on the climate would be remarkable.
We found that biofuels cut soot emissions into half, which is quite a massive decrease, reducing the amount of ice in contrails and also reducing warming from contrails by about a quarter.
In 2020, when overall traffic and the economy were greatly reduced worldwide due to the corona pandemic, this had a significant impact on air quality. But it was mainly the decrease in nitrogen oxides that was measurable. The colored gas, which is to blame for the visible layers of smog over many large cities, decays after just a few hours. Carbon dioxide, on the other hand, is long-lasting. If it's not absorbed by sinks, much of the emitted CO2 can remain in the atmosphere for 1,000 years, and newly emitted carbon dioxide gets added to the old. Nevertheless, CO2 is extracted from the atmosphere every day, through plants, organisms, and the sea. More plants could therefore remove more CO2 from the atmosphere. Reforestation and renaturation would also benefit nature conservation.
For me, climate change is part of environmental protection, to preserve this immeasurable wealth that we have as a task for humanity. And humanity is controlling its own destiny. And indeed, in my view, biodiversity and biodiversity conservation seem to be somewhat underrepresented. Climate change plays a role, of course, there's no question about that. Ecosystems are altered and climate change creates favorable or unfavorable conditions for species, and that keeps changing. Intervening directly through large-scale deforestation could easily be avoided, and very quickly. And this would have a very, very quick and direct effect. And climate is something that happens over decades, 5 decades. But many things we can prevent immediately.
Especially peatlands, which have been largely drained in Germany, store large amounts of carbon, about 6 times as much as forests, as long as they are intact. Due to the water and the lack of oxygen, biomass production here is greater than its decomposition, whereby carbon dioxide is bound. Protecting and restoring these threatened ecosystems would make a major contribution to climate protection in the long term and provide a habitat for many rare species. However, such nature-based solutions need a lot of time and large areas, both of which are rare.
Renaturation is certainly an important step in removing CO2 from the atmosphere, but all serious studies show that it is not enough. The spaces are simply not there. You can't collect all the CO2 through afforestation, for example, that we should be collecting, actually. And in this respect, it is an option that is certainly also well suited for other things, such as the protection of biodiversity, but it will be far from sufficient. And that is why we will probably not be able to avoid using technical solutions.
Such technical solutions mainly consist of filtering CO2 from the atmosphere using machines and storing it. Carbon capture and storage, CCS for short. This is a controversial concept because the technology is expensive and energy-intensive, and this energy must, of course, not release any additional CO2. The question is, what do we do with the filtered CO2? One approach is injection, in which case CO2 is pumped into deep rock layers under the seabed. Norway already uses this method in the North Sea. However, there is always a residual risk that the CO2 will be released again through leaks. Other companies have developed a more stable solution for this. At their plant in Iceland, the companies Climeworks and Carbfix remove carbon dioxide from the air, liquefy it, and inject it into deep layers of basalt rock, where the liquid containing CO2 reacts chemically with the volcanic rock and mineralizes. Thus, it petrifies by itself within a few years and can no longer escape into the atmosphere. Iceland has a location advantage. The use of geothermal energy is climate-friendly, and the porous volcanic rock enables mineralization in the soil. Conditions are not that favorable everywhere.
Getting it out of the atmosphere is not a problem. It can be done. The question is, what do we do with it? Do we want to bury it somewhere, which I personally would not favor, or do we want to use it as a raw material? There are interesting technologies to reuse what we extract. One key term in this context is the so-called synthetic fuel.
CO2 can be recycled. That's exactly what is being done on the roof of the Swiss Federal Institute of Technology in Zurich. Here, fuel is created from air and sunlight. The mini refinery with the large parabolic mirror sucks CO2 and water directly from the air and converts them into syngas, a mixture of hydrogen and carbon monoxide, in a thermochemical process using concentrated solar energy. Methanol, kerosene, and other liquid fuels can then be produced from this.
This means that you can actually use the CO2 from the atmosphere to produce so-called synthetic fuels, which in turn could be used, for example, to power airplanes. Of course, CO2 is produced again during combustion, but if we were to get it out of the atmosphere again, we would have a cycle where no more CO2 is actually produced on a net basis.
One advantage would be that the synthetic fuels could be used for conventional combustion engines, without major technical adjustments, at least in theory. So far, the quantities produced in the research refinery are far too small. But plans for the production of industry-relevant quantities are already being planned. A large research facility is located at the German Aerospace Center research site in Jülich. On an area of 80,000 square meters, more than 2,000 movable mirrors focus the sunlight onto 2 solar towers. One problem with the process is the large loss of effect. In the production of synthetic fuel, sometimes only 10 to 15% of the original energy remains. With electric motors, about 70% remains usable. So, this approach alone cannot solve the energy problem. Even if renaturation, CO2 storage and recycling can help to still achieve the goals of the Paris Agreement. The warming of the Earth has already progressed so far that adaptations to climate change are already unavoidable in many places. The researchers at the Helmholtz Center in Leipzig have noticed this too. Among other things, they use their forest models to find out how the forest reacts to different climate scenarios.
There are forecasts for the future that range from 1.5 to 2 degrees Celsius to 4 or 5 or 6 degrees Celsius. Of course, it depends on us humans and on how we behave in the future. And we put these scenarios into our forest model and saw that a forest can buffer the climate scenarios with 1.5 to 2 degrees Celsius quite well. The forest can still handle it quite well and maintain its ecosystem performance. If it goes above 2 degrees Celsius, you can see that the forest is too stressed, that too many trees die and are no longer photosynthesizing. That's why I really see a limit at 2 degrees Celsius.
After the dry years between 2018 and 2020, it's clear to many experts that spruce monocultures do not stand a chance in years like those. Forest conservation in Germany will require more mixed forests, but exactly what they will look like is not yet clear. According to the Intergovernmental Panel on Climate Change, 30 to 50% of the planet's total land area would need to be better protected and used less intensively to withstand the additional pressures of climate change while maintaining its ecosystem functions.
There are 2 major questions we face. One is, what can we do today to deal with certain effects that are coming? And the other is, what can we do to break and reverse the long-term trend? And you have to completely separate these 2 things from each other. So we have to make policies to change the climate in the long term, to reduce the human impact, and at the same time we have to take precautions for the things that are inevitable, which means we have to provide rivers with outlets during flooding. We cannot simply pursue a high dike policy. We have taken away a lot of land, also from the rivers, where we have settled and built industrial parks as well. But if at some point a dike breaks and the industrial area is underwater, then we have a natural disaster. But it is also a man-made catastrophe because we have made the decision to cultivate this land area in this way. And that's where we need to change our thinking.
Rivers are straightened and narrowed until they resemble canals. During floods, the river has no room to spread and floods streets, buildings, and sewers. By now, efforts have started to change back certain sections of rivers to the way they were. For example, an 8-kilometer stretch of the Isar River in the middle of Munich's urban area has already been widened and renaturalized. The river has more space, develops less pressure during heavy rains and floods. At the same time, this creates recreational areas for the population and urgently needed habitat for animals. Measures like these are expensive and by no means possible everywhere, but they could nevertheless help mitigate life-threatening situations and financial damage. Cities where more than half of the world's population lives must also be adapted to climate change. Heat waves, heavy rainfall, and water levels must be taken into account during building projects in order to protect people and infrastructure in the future.
The fundamental question we ask ourselves today concerns our behavior. We are overusing oceans, land, and the atmosphere, which has essentially become a pre-CO2 dumping ground. This results in a kind of geological timescale of the Earth's system with which humankind is unfamiliar and to which we are unable to adapt. That's why we researchers keep repeating time and again. There will come a point when we are no longer able to make predictions and lack the knowledge to cope with the extreme weather that we're experiencing.
CO2 avoidance, technical solutions, adaptation, and nature conservation. There will probably have to be a mix of measures to counter climate change. But without a long-term rethinking of how we use natural resources and our planet as a whole, new crises are bound to arise. Or is there another way out? Will humans be left to escape into space? There are probably many Earth-like planets in the universe. However, Earth-like does not necessarily mean habitable. For now, planetary research is satisfied with celestial bodies made of rock with a sufficient mass which have a spherical shape. Planets outside our solar system are so far away from Earth that they could not be reached even within several generations. One planet to which humans could actually fly is Mars. The journey to our neighboring planet would only take a few months. What awaits travelers there, however, is anything but life-friendly. Despite an intensive search, a planet B on which humans could find a new home has not yet been found. It looks like we'll have to make do with the Earth after all.
There's also research on this, and it's very exciting. It asks the question of how we humans could live in space. Can we colonize other planets? Can we make ourselves independent of plants, for example, or of the sea, or of the air? Do we perhaps have processes that can replace everything that nature offers using technical solutions? But that looks pretty puny when you reflect on the actual state of affairs. What I'm just following with enthusiasm, this question of terraforming, finding space on other celestial bodies, and the question of whether we can build Planet B, a second Earth, it always comes down to this. We should rather take care of our own Earth, and we are still calling the shots for doing it well within the next few decades.
Planet B could only exist, I believe, in our own planetary system, and in this respect, the best investment is in Planet A. And I would invest in Planet A and look at the other planets around us scientifically. That is highly exciting, and that will certainly also help us with regard to Planet A. But to fly to another star system, now that, I think, really is science fiction.
The view from the outside still opens up new perspectives, a sense of the big picture. Space travel has taught people a lot about the Earth and about its own role in the Earth's system. Now it's time to put this knowledge into practice. With the Apollo 8 mission, humankind also discovered its own planet. Half a century later, it has to realize that it's the only oasis in the darkness, the only good planet.